Hello everyone, this is Dr.Hira, and in this lecture we are proceeding our discussion for the reactions of alkenes and the reactions of unsaturated hydrocarbons. So our previous discussion was about what kind of reactions the unsaturated hydrocarbons undergo, and we have covered the overview that how the pi electrons are responsible for giving you the number of different um, products, and that's why these reactions have assigned particular descriptive names to these ones. So today I'll focus mainly on oxymercuration reduction, one of the a little complex multi-step reaction, and it's not as easy as the addition of the halides on the alkenes and alkynes. So that's why I selected this reaction, that we can focus on its mechanism, step by step, how that reaction proceed and what are the overall product when we go through the oxymercuration reduction of an alkenes. So before going into the mechanism of oxymercuration reduction reaction, those, I wanted to discuss the reaction mechanism with you, just to refresh if someone is not um, very much clear about what the mechanism is. So we talk a lot about the reaction, chemical reactions, the type of chemical reactions, and the reaction equations. So if you are looking for more details about the chemical reactions, so you can check out my lecture on my YouTube channel with the title Chemical Reactions, in which I have discussed the different types of chemical reactions. So we talk about the chemical reactions means whenever there is A plus B, that is a reactant, and that is undergoing some of the reaction. That could be the addition, that could be substitution, or any kind of reaction, and eventually we got a product. How we mention that chemical reaction in a mathematical form or in a symbolic version, that called the chemical equation. Now there is another terminology, which is the reaction mechanism. So mechanism is basically a step-by-step description of the chemical reaction, in which we give the whole pathway, uh, the whole supposed pathway, that what we understand, that what kind of different transitions reactive is undergoing to reach the destination of that actual form of a product. So you can say this is the itinerary of your of any of your trip, that if you want to fly from London to Paris, if you wanted to fly from Lahore to Islamabad, so how you are moving and how you are going to that location. So that exact pathway and the all details are basically the mechanism of the reaction if we apply on the chemical reactions. So here I have mentioned one of the reaction. So there is A plus B, that is a reactant because that is the or starting material. So sometimes we refer it as SM because this is our starting material with which we are conducting some kind of reaction. So we may use other reagents, we may just heat it up, or we may do some of we are passing through some of the gas, so it is converting into a product. So this is just a generic equation. It doesn't mean a reaction. It just to give you the idea that A plus B are the reactants which are going through the sum of the conversion. So there was a C, then that further modified into the D form, and eventually the X is our product. So the C and D is between the transition between the A plus B to the path of the X as you take the transition flights most of the time. So the transition state is basically, this is something to bringing you the reactant to the product in its form. So I have mentioned the transition state slash intermediate. So the transition state and intermediate, they have the difference of the lifetime. If the transition state is more stable, it has the good lifetime of few seconds. So it means that can survive in the system for a longer time, and that is basically the species which is available for the attack to convert into the product one. So the intermediate is basically the stable transition form, and the temporary modifications of the reactants to reaching the point of their product is basically the transition state. So that will be more understandable for you when I'll share with you the next slide. So there, the transition state, in another way, we call it as the highest energy point on a reaction coordinate diagram. So I will talk about what the reaction coordinate diagram is. So the chemical structure at this point is commonly called the activated complex. So another term by which you can understand what the transition state. So this is basically the excited state. This is basically the activation complex which has formed from the reactant after some kind of reaction conditions. That could be the heating, that could be the stirring, that is the reaction mixing or collision kinetic, or the energy collision with another reagent. So basically when the reactions are occurring, so there is a number of different collisions which are happening between A plus B, and then they uh, they modify their structure in a way that that has converted into another form as a product. So you can understand in an example that if we jump on a branch of a tree, so there is a certain amount of energy which we are providing to that branch. So if we keep on jumping, so that branch, if it is more stable in its horizontal form, so that will go through some of the bending position, right? So this is basically the transition it goes through. But if I keep on jumping even for more time, so then it means that has attained its maximum point. So that deformed bending position is when it cross its limit, so that will just break broken, that has broken from the tree. So in a mean same manner, so the reactions are happening that when we are mixing the two reactants, so they collide with each other, and sometimes we provide the more heat for enhancing, increasing that kinetic energy and that collision between these two. So by hitting with each other, so this show is resulting in a product formation. So the transition it is going through, the activation it is going through is called the transition state, and if that is a little stable, so that is called the intermediate. So now this is a reaction coordinate diagram. So the chemists basically use that reaction coordinate diagram to understand the mechanism, that what are the different energy barriers a reactant is passing through, what are the different structural changes a reactant is going through. So that through the reaction coordinate diagram, the chemists are able to devise or develop the mechanism of certain reaction. So now I need your attention for this figure that you have. If you just look at this, so on the y-axis we take the energy, and that is usually the Gibbs free energy, the heat or the energy of the reaction. So we plot that one versus the reaction coordinate. So that reaction coordinate is basically the structural changes which the reactants are going through with the passage of time, and we are examining these by using the different tools, though that is not the right now the our discussion. So you have to focus that when a graph is plotted between the energy on a y-axis and the reaction coordinate on x-axis, this is called the reaction coordinate diagram. So here, if you just look at this one, so A plus B is basically our two reactants. And firstly, we will strictly go at what is happening in that reaction. So the A plus B are converting into the product, which is the C plus D. So that is the net chemical reaction. Now we have to see that what is the mechanism and what is the reaction coordinate. So basically A plus B has passed through some of the energy barrier, and that is called the activation energy, which is for its activity to convert to another transition state to reach the point where it convert into the product one. So this activation energy, the first barrier it has covered is the transition state one. Now there is the dip in between these two heaps is the intermediate, and there is another transition state two. And here, this is having another activation energy if we compare from the intermediate. So this is the activation energy two, right? So basically what it illustrates is this diagram is basically giving you the idea of a two-step reaction. If we have a two-step reaction, it means there are the two transition states. So it means the reactant is going through the one transition, then there was an intermediate, which is a stable form, right? It is staying for some time. This is a stable form, and now it is easily available for the conversion into that product. And it going through a minor, another activation complex and a transition state, so that can adjust itself into the product form. So now if you just look at the energy, so the maximum energy is of this transition state. And if we compare, the intermediate is at the minimal energy between these two transition states. So it has the least energy. So the least energy transition state is basically the most stable one. And this transition state, which is having the highest activation energy, is basically the rate determining step, because this is the slow one, and this has to pass through that activation energy gap. So the maximum time of the reaction is basically to achieve that target. So that is basically the rate determining step. So the reaction rate of a reaction will be started on the basis of that reaction rate determining step, which is having the higher activation energy. So you should keep these concepts in your mind. So now we will talk about, and if you compare this reaction, so this reaction coordinate diagram also give us the idea that either that reaction is the exothermic or endothermic reaction. So now if you just look at this energy point of compare the product versus the reactant one, so reactant energy is at this scale, right? And if you just look at the C plus D, which is a product, so this is less than the A plus B. It means the reactants has to lose that amount of energy to convert into the product. It means the energy is releasing to the system, right? So that's mean that is the exothermic reaction. And the delta H sign is basically the positive one. Now, the reactive intermediate. So we talk about the transition states and intermediate. So intermediate is basically, as I said, that this is having the minimal energy between the two transition states. So we are basically discussing the organic chemistry. So in this discussion, all reactive intermediates are the forms of the carbon which will be formed, because there is a double bond between the carbon. So, or reactive intermediate are something which is having the forms of the different carbon excited forms. So there are the three different forms which can exist as a reactive intermediate in the form of in terms of the carbon. So here, though in all reactions which we will discuss, this is basically the carbocation, but you should know that in what forms the reactive intermediates can exist if we talk about the carbon. So the carbocation is basically the carbon which is deficient with the 2 electrons, and it is only making the 3 bonds, so there is the need of another bond with that one. Now the radical is when the carbon is having the 1 unpaired electron, and it is still deficient with 1 electron. Now the carbon anion is basically the carbon which is having the 2 extra electrons, So if you count these, it's electrons, Lewis electrons. So these are the 2, 4, 5, 6, 7, 8, and this negative sign is basically also mentioning the electron. So that's why this is acquiring that negative sign, because it has gained an extra electron to complete its octet one, but there is still the deficiency in the bond of the carbon. So obviously these are the abnormal bondings of the carbon. So it has to go through the normal bonding. It has to get its complete its octet one. So that's why these are very reactive species, and they can certainly uh, go for the next step to convert into the product one. So that's why they are the stable somehow, if we compare the other species, because they do exist for some seconds in a system, and they exist as an intermediate, and they are very reactive because of their abnormal bonding, and they have to go through their normal condition. So rate determining step, I have already mentioned you the step in a multi-step reaction, the slowest step. And the slowest step is this one, that one which is covering the highest energy barrier. Now, that was the overview sheet for the reactions of the alkenes. And now in this lecture, we are discussing the oxymercuration reduction reaction of the alkenes one. Here, the oxymercuration reduction reaction, as the name states, you may get some of the idea that there is oxygen containing, there's oxygen which is adding, there's a mercuration, and means there's a mercury metal which is involved, and eventually that will go through the reduction. So yes, there are basically, we are using the reaction reagent. So this mercuric acetate is will be used, which is the source of the electrophile, and the alkene which we have as a nucleophile, because it is having the pi electrons and it is looking for the electron deficient source where it can make another bond. It can easily make another bond through these pi electrons. So this oxymercuration is giving you the source as a electrophile, and the reaction will happen in the water medium, which water is as a solvent, and it is also working as a nucleophile, which you will see in the mechanism. So the sodium borohydride is basically the reducing agent we are using, because firstly that will go through some of the intermediate steps, and eventually that intermediate has to reduce to convert into the normal stable product, and our final product will be the alcohol. If we react the alkene with the mercuric acetate in water medium, and we provide and we react later with the sodium borohydride. So another thing is, in this net, this is the overall reaction what we get from the alkene by treating with these reagents, and the product is the alcohol one. So now there is a term which is called the racemic mixture. So racemic mixture is this one when we don't have the single form of the product. So though the chemically in IUPAC name the product the same, but these are having the both isomers of each other. So one is the S isomer, another one is the R isomer. So S isomer is that one in which the arrangement of these groups, bulky group on the chiral carbon, the carbon which is having the 4 different groups. So here, if you just look at this, the carbon is having the hydroxyl carbon has the methyl group, carbon having the 1 hydrogen, and carbon have that rest of the chain. So this carbon, if the arrangement of these high priority groups is in counterclockwise, this is designated as S, and if that is the clockwise, so we assign this R, right? So that is another topic, a full-fledged topic, which we can discuss later. But right now, at the moment, you should know that we will get the product, which can be separated by different techniques. But the overall product is alcohol, but we do have its both isomers there, S and R. So there is a need that you should know that what is the structure of the mercuric acetate is. So if we open up that structure, so the mercury is bonded from the both side with the acetate side, and you know the acetic acid formula is CH3, C double bond O and O, H, right? So by removing that hydrogen, this is making a bond with the mercury. So this is a mercuric acid. So you can write its condensed in the shorter form in that way, or even the more condensed form is this mercury, and in a bracket you are just putting the two value to mention that they are the two acetate side on the both side of the mercury. So this is a mercuric acetate. Now we will go for the mechanism. So we have established one thing, that when we treat alkene with the mercuric acetate in the presence of the water as a solvent, and later we treat it with sodium borohydride, so the overall product will be the alcohol one. But we have to see that what are the different steps this reaction is going through. So in mechanism, we use the pushing arrows. We use the different arrows direction to give the idea which is the electron source, and which is a nucleophile, which is electrophile, and how that reaction is proceeding. So that is basically giving you the idea about the mechanism. So the very first step is this one, that we are using the mercuric acetate, and we know that we have to dissolve it in a water medium, which we are using as a solvent. So the mercuric acetate ionized in a form that it gives the mercuric acetate cation, and there is the acetate anion, right? Acetate anion. And this mercuric acetate with the positive sign is basically the electrophile. So now electrophile, we have discussed that one, that it is looking for the electrons to make a bond, and the nucleophile we have in our system is the alkene one, which is our starting material, which is our object to convert from the one functional group class to another product. So now the step 2 is make a bond between a nucleophile, pi bond, and an electrophile. And we know this is the electrophile and this is the nucleophile. So it attacks on this side, and these pi electrons will make a bond with that mercury. Now, the very interesting thing about this mechanism is that there are the possibility of these three contributing structures. Now, through the studies, mechanistic studies, that has established that it go through this intermediate, which is the most stable one. So that's why it has written the major contribution, the major contributor structures, right? And this structure is termed as the bridged mercurinium ion intermediate. So this is a mercurinium ion because that is forming cyclic, temporary cyclic, three-membered cyclic structure with that one. Now, this form is, it's an open carbocation intermediate in which this carbon is the secondary one. So let me use a pen here to mention you that what we are going to say this, right? So this is the secondary carbocation. And if we compare this one, this is the primary carbocation. So 1 knot and 2 knot, right? So secondary carbocation is that one, the carbon reactive intermediate, which is having the electropositive charge, but this is bonded from both two sides with the R groups. There is R group and there is the methyl group which is attached to this one. If we just look at this one, this carbon is only bonded from the one side with another R group, and this is the primary one. So when we compare the primary versus the secondary or the tertiary one, so the secondary carbocation is the more stable than the primary one, and the tertiary carbocation, in which the carbocation will be bonded from the three side with R groups, will be even stronger and the stable than the secondary carbocation. So right now we have the only the possibilities of the two. One is a primary and the other one is a secondary one. So this secondary carbocation is more stable as compared to this one. So that's why this structure has a negligible contribution, and this is having the minor contribution. But the most contributing structure is basically this mercurinium ion intermediate. So that was important to mention you, because later that ring will open up and that will go for this one, right? So we will focus on it, that what is that particular product and what was the possibilities and why this is selective reaction. So here, if you just ignore these both forms, so you can directly write that attack of this mercuric acetate cation on this carbon, doubly bonded carbon, is basically forming this mercurinium ion intermediate. Now, the third step is basically, we know that in this reaction system, we have the water molecule, and this was the intermediate which has established, and still there is a carbon which is having the positive sign. And there is a question from you, that which carbon will have the more opportunity, which has a more you can say them has a more probability for getting the positive charge. I have just discussed in the previous slide. We can take a moment. Okay, yeah. So if we just compare these both carbons, so this carbon is a secondary. So the possibility and the highest the priority of the opening of the structure is this one, that it convert into the structure that this will get the positive charge, and this acetate, mercury acetate side, is hanging up with this carbon, right? Because this is the lighter side, this is the primary carbon, this is the secondary carbon. So secondary carbocation is a more stable than the primary one. Now this water molecule, through this oxygen electrons, which is also a nucleophile, will attack on this carbon, and here this is bonded with this one, right? Now this addition is basically anti-addition. Why it is called anti-addition? Because this water molecule is attaching from another side, and this mercuric acetate has attached to the opposite side. So they are just trans to each other, they are just opposite to each other. So that's why this is called anti-addition of mercuric acetate and water molecule. Now the fourth and the last step of this reaction mechanism is this, that this is the basically mercuric acetate is still hanging with this one to make that bulky one, and it has to convert, it had to cleave, because this is a good leaving group, and then that species will reduce into the final product, right? So we know this hydroxyl has attached on this carbon, which is the substituted carbon, and this is the less substituted. So we choose a term substituted carbon, means which is more surrounded, or which is bonded with the more R groups as compared to this carbon, because this is just surrounded with the two hydrogens, right? So the nucleophile will attack on the carbon which is having the more substituted side. So we also have discussed the one thing, Marconic addition and anti-Marconic addition. So you have to think about this one, that either that addition is a Marconic or anti-Marconic. I will answer you at the end of the lecture. So here, the sodium borohydride, as I have told you, that this is a reducing agent. It means that will reduce other species. So it will reduce that carbon by giving the hydrogen to this side, right? And here it will also contribute the hydrogen to acetate one, and this acetate will convert into the acetic acid as a byproduct of that reaction. So here the overall product is this one, that we get the alcohol from that intermediate, right? So this carbon got the hydrogen from the sodium borohydride, and this mercury from the +2 has converted into the zero form. So this mercury has reduced by accepting the 2 electron, because at this, that was the +2, and here this is the at 0, right? Though we have mentioned that note, means that has converted into the elemental mercury from the +2 to 0. When a species is gaining the electron, so this is basically reducing, or it is accepting the hydrogen. This is the reduction form. So now elemental mercury and or alcohol, and another thing is the acetic acid. So this acetate is removing from the mercury, and we get the acetic acid as a product, because in our water system that can easily convert back to its acetic acid side. So this acetic acid is producing in the both steps when this attack, and there was acetate which cleave from this side, and that is acetate anion converted into the acetic acid, and another molecule is producing when the other acetate anion is cleaving that mercury, and this mercury is converting into its elemental mercury form. Now, the task is that you have to write the mechanism of the following reaction. I have mentioned you the product in the same way, that there is a Resumix mixture. So the overall product is the alcohol one. The conditions are the same. Now you can easily envisage or you can easily draft the mechanism that how, what are the different steps this alkenes will go through, and how this is uh, converting from the alkene to the alcohols one. Now, the question I was asking you, that either that reaction is following the Markovnikov addition or anti-Markovnikov addition. So Markovnikov addition states that the nucleophile or the addition will go on that carbon, the hydrogen will attach to that carbon which is already rich in a hydrogen. So it means when the hydrogen is attaching on that carbon which is already have the more hydrogen atoms as compared to this one, and the nucleophile is attaching on that carbon which is the more substitutive one. So this is the Markovnikov addition, right? Another simple thing is you can do is that you don't need to write this in a both form if that is not have asked you to mention the stereochemistry. So you can just write with the bond that this is the alcohol, but just mention that this is a Resumix mixture. So you should keep in your mind if someone asks you and you have to go through the mechanism, so you should know that we will get the two kinds, the product, though the overall product chemical is the same, but their isomers are different. So we have to separate these isomers for the purity purposes. So you can just write the name and just mention in the bracket that this is a Resumix mixture, that we are having the both stereoisomers in a product. So that's your task you have to submit on a Moodle. So if you have a question, you can ask, I will love to answer. Have a good day. Thank you.